Welcome back. We are discussing about the wastewater treatment, under which we are discussing the secondary treatment options. In this video, we'll be talking about the secondary sedimentation tank after activated sludge process. So now this is the activated sludge process where we are having an aeration tank and then connected with secondary clarifier or secondary sedimentation tank. So we are calling as SST. So where wastewater is entering after primary treatment directly into aeration tank, and then it enters into clarifier. So here the biological solids, they will be settling down. A part of this sludge is now wasted from the sludge cycle, and then some portion is now returned back as the recycled sludge back into aeration tank, so that a MLSS of X is maintained. So now the after the sedimentation tank, the biological solids are settled down. The solids now will be leaving the secondary sedimentation tank with a solids content of Xc. So here what we are saying is this XR is very much greater than Xc. So the Xc value is very small, around 20 to 30 milligrams per liter. Whereas the XR, that is nothing but the recycled sludge, is around higher concentration, around 10 to 12,000 milligrams per liter. So now what you understand in this, the aeration tank as well as secondary sedimentation tank, together they are considered a single system. So now this part only we are talking, this part, the design part of the secondary sedimentation tank. So whatever is coming here, the flow rate is the discharge Q, and then because a Q is there, a QR is recycled back, out of which a QR is again going back. Effectively, Q is there in the SST, and the solids content is nothing but whatever the MLSS concentration X is coming, that will be there at the flow rate of Q. So we will talk about the design aspects, then we will take a small example also. Before we go for design aspects, we should look at the tendency of the settling in the sedimentation tanks. So here we consider a glass jar of the height of what we call as equal to that of sedimentation tank. And now the entire liquid is filled up to the top level, right? So now this is the interface between the solid and the liquid. Here at the initial phases, at time t is equal to 0, at time t is equal to 0, there is no interface here, there is no totally equal to h. After some time of settling, say t1, the interface is now changed here, so comes out somewhere here. After another time t2, this interface is now further reduced to some other point. Similarly, we are having T4, so T5, T6 here. So what you are seeing, if you note down these points and then try to join them, what you are seeing is the particles, how they are settling. Now, this is the line. This is how the line goes. So it is not straight like this, and it is not straight like this, but there is a small joint, the small joint here. What exactly is this? Now you try to understand from this picture here at the bottom. Here at this bottom, you see this till this part is linear, and beyond this part it is again linear. In between, some small change is there in the settling pattern of the solids. How you're understanding this is based on the depth of interface. So now let us try to look at what you call, we are having different types of particles. Discrete particles, where the size and shape of this particle, they are not changing during the process of settling in a particular tank. And second part is a flocculent settling. That means the particle which is having some small size, by the time it's come down to the bottom, its size and shape is now changing. So this is called discrete settling. This is a discrete settling, and then this is called flocculent settling. The flocculent settling will be coming for coagulation, and then discrete settling is considered in the process of plane sedimentation. So that means what is happening is in this particular point, because the particles are denser, now till some portion of the time, the settling is rapid and linear here. So this is we are calling as the discrete or flocculent settling. Now what is happening here? What is happening here? You can see beyond this point, what you see is the settling curve becomes non-linear. It is coming down like this. That means if you draw a line tangent here, this is a line coming from the top line, and this is the tangent from the bottom curve. So they are intersecting at some point here. Then if you draw a tangent here, perpendicular, it is intersecting to this hindered settling. So that means the hindered settling is somewhere between these two zones. Then what is the, first of all, we'll understand what is the compression settling. The compression settling means when you come to the bottom, you see here, when you come to the bottom of the tank, the interface height is not changing much. Why it is changing slowly at the bottom is nothing but here this settling is now almost completed. But when you are coming to these two stages, what happened is the particles which are there at the bottom, they will be compressed by the solids on the top, thereby some small amount of gap is created. That's what you are seeing here at the bottom in the line curve here. So what you see is the last of two stages, this is nothing but the settling, the interface gap which is obtained here. It is based on the overburden solids which are compressing the bottom solids. So that's why it is called as a compression settling. Between these two settling, what you are having, you are calling as a hindered settling. So this is linear, this is a compression in between. These solids, they are not completely separated from this process, and they are not completely undergoing the compression. The transition period is nothing but your what you call as hindered settling. So that is called as a type 3 settling here. And compression settling is usually occurring at the sludge zone, where there's already some portions are solids are settled, and still some more solids are keep on coming. They will try to compress these solids down. That's where the compression settling is going to occur. So we are having four types of settling now. In the water treatment section, we are talking about mainly discrete or flocculent, type 1, type 2. Whereas in wastewater treatment, particularly in the secondary sedimentation, we will be talking about hindered settling and compression settling. So now let us look about this terminology in a better manner. So same thing as talking here. Hindered settling, when the particles become crowded, they settle at a slow rate. This causes nonlinear velocity profile. That is what we are talking here between these two zones. These two zones. This is what I was talking here. So the particles are settling very slowly in this zone. Till this point, they're linear coming down, and here this is occurring due to compression. In between, the particles are settling slowly, going towards a non-linear rather than a linear trend. And there is a called free settling. Free settling is nothing but when there is no disturbance in the uh, sedimentation tank, and then particles, they do not interact with each other, so, they do not interact with the walls, so the particles are freely settling directly. So but we are normally looking at the hindered settling or compression settling. Compression settling is usually occurring, please remember, this will be at the sludgy settling zone, and hindered settling is somewhere slightly above the sludge zone, where the nonlinear velocity trend is going to be observed. This is what we have to understand before we go for the design of the sedimentation tank. The purpose of the sedimentation tank, if you look at, this is to remove the finer organic solids and biological solids coming from aeration tank. Now here, what we are trying to look at is the design is based on the solids loading and surface overflow rate. These solids are coming from the aeration tank, and surface overflow rate is mainly provided to clarify the liquid and solids, separate the liquid and solids. That is a surface overflow rate. Higher value which is obtained for the surface area based on solids loading or surface overflow rate should be adopted. And design should be made for average flow and checked for peak flow. And as I already mentioned, for the secondary sedimentation tank, after activated sludge process, the flow rate for design is based only on the initial flow rate Q. The parameters of design you see here, SST after ASP, the average flow for SOR is around 15 to 35 meters per day, and for peak flow, the SOR should not be more than 50 meters per day, 40 to 50, and depth should be around 3.5 to 4.5. And if the secondary sedimentation tank is provided for extended aeration, then slightly different values are there, lower values are adopted. 8 to 15 meters per day for average flow, 35, not more than 35 meters per day for peak flow, and depth is again remaining same. The most important parameter here is the solids loading rate. So for average flows, it should be around 100 to 150 kg per day per meter square, and peak flow, it should not be more than 250 kg per day per meter square. So please remember the area, surface area again depends on the area obtained for solids loading as well as for the surface overflow rate. Based on that, now we will identify the maximum value obtained as the surface area to be provided for secondary sedimentation tank. Now let us look at a design to understand these design parameters. Design a secondary sedimentation tank after activated sludge process to handle an average flow of 10 mld of sewage. The MLSS entering a secondary sedimentation tank is 3000 milligrams per liter. So you can assume suitable data. The average discharge, the A stands for average, and there will be peak flow. So therefore we will also write QP stands for peak flow. 10 mld is the average discharge, so 10,000 meter cube per day. Then this conversion first we have to do it. Then surface overflow rate 15 to 35 meters per day. So now I'm assuming 20 meters per day. So the area, surface area of the sedimentation tank will be discharge divided by surface overflow rate. So I'm dividing 10,000 by 20, I'm getting 500 meters square. Now I'm taking this as the first value. So area obtained per average flow SOR, right? Now first of all, we will calculate solids loading on secondary sedimentation tank. This is nothing but flow rate multiplied by MLSS. How much is solids loaded now? 10,000 meter cube per day. This is average flow rate into 3000 milligrams per liter, right? This is the solids loading coming on MLSS. Now convert from meter cube to liter, 1000 liters per meter cube. And now the milligrams are coming here. Milligrams should be converted to kilogram. So 10 to the power of minus 6. So it comes out to be 30,000 kilograms per day. So now the solids loading rate for average flow is around 100 to 150 kg per day per meter square. So now I'm assuming the maximum value of say 100 150 kg per meter square per day. So therefore the surface area will be equals to 30,000 kg per day divided by 150 kg per meter square per day, which comes out to be around 200 meters square. So now this is the surface area obtained for solids loading under average flow. Now we should also check for peak loading. Peak loading normally it will be around 2 to 3 per wastewater flows. So I'm assuming a peak loading rate of 2. So 2 into 10,000, 20,000 meter cube per day is the peak flow. So the solids loading at peak flow will be equals to what? Peak flow is 20,000 multiplied by 3,000 milligrams per liter, and again 10,000. This is the 10 to the power of 3. That is 1,000 conversion from meter cube to liter, and this 10 to the power of 6 is conversion from milligrams to kilograms. What I'm getting is a 60,000 kg per day of solids loading at peak flow. Solids loading rate under peak flow conditions is 250 kg per day per meter square maximum. So within this region, now I'm assuming 200 kg per day per meter square. In such a case, this area will be equal to 60,000 divided by 200, which is equal to 300 meters square. So now the area to be provided, it should be based on the maximum of these three values. This 500 is coming for surface overflow rate under average flow. 200 is coming for solids loading rate under average flow. 300 coming for solids loading rate under peak flow. The maximum is 500 meters square. So let us go for a small check. What is surface overflow rate if we adopt 500 meters square of surface area at peak flow? So peak flow is 20,000 divided by 500 meters square. This comes out to be 40 meters per day. This is within the range of 40 to 50 meters per day permissible peak flow SOR. So that is okay. No, within the range. Now the diameter we are calculating for 500 meters square, which comes out to be 25.3. Let us assume we round it off to 26 meters, so that the maximum permissible diameter is 30 meters. And the range of depth, if you look at 3.5 to 4.5, so I'm assuming 3.5. So now let us calculate the volume of the secondary sedimentation tank. So area multiplied by depth, pi by 4 d square into h, which comes out to be 1858 meter cube. And detention time, we are calculating as V by Q. So volume multiplied by 24 hours. This is converting again days into hours. Comes out to be 4.45 hours. And wear loading is Q by pi d. Q is 10,000 average flow divided by 26 is the diameter. Pi is a constant. Pi d is the circumference. So it comes out to be 122.5 meter cube per meter per day. Now let us look at the bottom slope. Look at the bottom slope. This is the sedimentation tank. Now you can see here in this sedimentation tank. Now this is the diameter, central diameter 26 meters. Liquid depth is 3.5 meters. We will keep some 0.3 meters freeboard. Now we have to calculate this particular portion. This particular portion is what we have to calculate. The depth is what you have to calculate. Usually the depth is provided as 10%. So 10% means what? So this is 10% slope. So now I am calling this as y. So this will be equals to what? D by 2. D by 2. So this is your 10% slope. So y by d by 2, y by d by 2 is equals to 10% means 10 by 100. Using this value, I'm calculating y is equal to 1.3 meters. 1.3 meters. So the total depth of the tank will be equals to freeboard plus the liquid depth plus the hopper bottom and the sludge collection. A total will be equal to 5.1 meters. This is how we normally calculate the a simple calculation, the secondary sedimentation tank based on surface overflow rate and solids loading rate. And the most important thing you should understand is this secondary sedimentation tank design, particularly when you're talking about the different types of solids which are settling down, and we should talk about the hindered settling as well as compression settling. Compression settling is occurring at the bottom zone where 1.3 meter depth is occurring, and hindered settling is slightly above that. And clear water will be there beyond that particular depth. So this is how we look at the design of secondary sedimentation tank and the design principles of secondary sedimentation tank involved. Thank you.